today we're going to talk about partitions, and the goal is going to be to relate them to the equivalence relations that we've been talking about over the last couple days. And so the idea of a partition is relatively intuitive, but as per a lot of things, the mathematical definition is a little bit formal and stodgy. And so the idea is that you have some set X and you're just going to divide it into other sets. The formal mathematical definition is that you're going to divide X into a collection, script A, of subsets of X, where each one of these subsets you divide it into, so the A's inside your collection, all of them are non-empty. And then the union of all of these sets gives you back the original set. And also, anytime that you take the intersection of two of the sets in your collection, if the intersection is not empty, then the sets themselves must be equal. And so that's just saying more intuitively that each element in X can only go to one of the subsets in your collection. And so if we talk about each of these properties from a more intuitive perspective, the first one is just saying that every grouping in your collection needs to be non-empty. The second one is saying that everything in your original set needs to be placed into at least one of the subsets. And the third thing is saying that every one of the things from your original set is placed in at most one of the subsets that you choose. And so in other words, a partition has each element of X appearing in exactly one of its parts. This will be a lot clearer if we just look at an example. And so if we look at how many partitions there are of the set bracket 3, and so first of all, I should remind you that bracket 3 is notation for the set 1, 2, 3. And so this is just asking how many ways can we break up 1, 2, 3 into smaller sets where everything is still there. And so one option would be to just leave it as it is. And so my collection of subsets of X is just the entire thing. There's just one of them. Another option would be to say that we're going to have 1, 2 stay together and 3 be by itself. And you could see that we could do this sort of collection in 3 different ways, where we could have 1, 3, and 2, or also 2, 3, and 1 being separate. And so in other words, I just listed all the ways of partitioning my original set into exactly 2 other sets. And then the last option would be to have every element be all on its own in an individual set. All right, and so each one of these are partitions because, again, if we compare to the original set that I had right here, then you could see that 1, 2, and 3 were always assigned to at least and at most one of the sets on each line. And so it is a sort of fair division of everything, and that's what we're calling a partition. All right, so now I want to look at a slightly more complicated example. And so here we're going to look at how we could break up the set 1, 2, 3, 4 into other sets. And so we could write out all of the possibilities by hand, but as you can imagine, if we were talking about the set from 1 to 10, that would quickly become painful. And so I'm going to try and tell you a strategy that would help for larger things, although we could still do it by hand here by just listing them all out. And so the idea is going to be we're going to consider how many ways we could break up 1, 2, 3, 4 into just clumps of varying sizes. And so I'm not going to worry about what's inside the clumps yet. I'm just worried about how big the clumps are. And so, in other words, I could have one clump of size 4, which would just be the entire thing. Or I could have a clump of size 3 and a clump of size 1. Or I could have a clump of size 2 and another clump of size 2. Or I could have a clump of size 2, a clump of size 1, and a clump of size 1. Or I could have 4 clumps of size 1. And so these here, if I'm talking a little more formally, these would be the part sizes because these are the parts of the partition. And now for each one of these categories, I want to talk about how many ways are there to come up with a partition that matches this category. And so in particular, for the clump of size 4, we already know that that would just be the entire set. And there's only one way of doing that. And so the number of ways to do this is just 1. For the 3 plus 1, For example, I'm talking about something of the form 1, 2, 3, and then 4 by itself. And if we're trying to figure out how many ways there are to do this, then you could tell that the only thing that matters is which number is by itself. And as soon as I've decided which number is by itself, then the rest of the partition is determined because it all has to be lumped together. And so in this case, there's going to be 4 ways of doing that. The next thing would be 2 clumps of size 2, so a 1, 2, and a 3, 4. And this one is a little bit harder to count. And so the idea is I need to choose which 2 things go together in the first one, and then by default, the other 2 things would need to go together. And so if I choose the 2 things that go in the first bracket together, then I could see I have 4 choices for the first thing and 3 choices for the second thing. But there's an issue because if I choose 1 then 2, that would really be the same as choosing 2 then 1. And so I need to divide this by 2 to account for the fact that the order doesn't matter within the set itself. However, it turns out that that same sort of reasoning that the order doesn't matter is also true in this case for the 2 sets themselves. Because if I choose the set 1, 2, and then I have 3, 4 as the leftover set, that would really give me the same partition as if I had chosen 3, 4, and then had 1, 2 be the leftover set. And so for that reason, again, I actually need to divide by 2. And so I could simplify this, and you can see obviously the 4 in the numerator is going to cancel, and so there's 3 options here. All right, for the next one, let me write down another sample of what I'm talking about. And so this one is a similar sort of analysis as to the line above, where first what I might want to choose is which 2 things go together. And so if I choose the 2 things to go together, just like last time, I'm going to have 4 times 3 over 2 choices for how to do this. But unlike last time, now there is no symmetry between choosing the 2 in here and then choosing the 2 things that are by themselves, because those are different partitions. And so at this point, there's no need to divide by 2 again. And so here I will have 6 different options for this category. And then the last choice here is just if everything is all by itself. And of course, there's only one way of doing this. And so we'll get a 1 here. And now I can add up all the possibilities from this column. And so if I add this up, I can see I have a 6 and a 4. And so that gives me 10. And then I have a 3, a 1, and a 1. And that gives me 5. And so in other words, the total number of possible partitions is 15.